Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 1st, 2025, about 3 days ago. This paper introduces a framework that teaches Llama 3 to reason, achieving an impressive 81.8% accuracy on the challenging Math 500 benchmark. The paper is titled ASTRO, Teaching Language Models to Reason by Reflecting and Backtracking in Context 2507.00417v1. And as we'll see, the key is teaching the model to think more like a human problem solver, even correcting its own mistakes. The authors show how to systematically instill these reasoning skills, like self-reflection and backtracking, into open source models. Alright, so this first figure really captures the core idea. On the left, you see a standard Llama 3 model, giving a step-by-step answer. But it's wrong. After the ASTRO training, the model's reasoning, what's called its chain of thought, is totally different. It actually pauses to ask, wait, is this correct? And then backtracks. This is taught through 2 stages. First, supervised fine-tuning, or SFT, where it learns these patterns from examples. Then, reinforcement learning, or RL, where it's rewarded for using those patterns to find correct answers. The bar chart shows the results of this process, with massive performance gains across tough math benchmarks. So how do they actually teach the model to do this? This figure breaks down the entire ASTRO framework. It starts with a process called Monte Carlo tree search, which is a way of exploring all the different paths to solve a problem, like branches on a tree. Each step gets a quality score, so the system learns which paths are dead ends. Then, in a step called procedure cloning, these search paths, including the mistakes and corrections, are turned into a natural language thought process. This data then trains the model to reflect and backtrack, leading to those big performance gains. Building on that framework, this table then details the data used for the supervised fine-tuning stage. You can see they pulled problems from several tough math datasets, like MathTrain and Numina-Math. But look at the numbers. For just a few thousand problems, they generated tens of thousands of solution trajectories. A trajectory is just one of the many possible paths to an answer. And critically, these paths include thousands of backtracks and restarts, which are explicit examples of the model realizing it made a mistake and correcting itself. This is the core data that teaches the model how to reason. Moving to the results, this table really shows the payoff. We're looking at performance on several math benchmarks. You can see the baseline Llama 3.1 model, and then the versions after the 2 stages of ASTRO training. The key metric here is pass at 1, which means getting the answer right on the very first try. On the Math 500 test, the final ASTRO model after reinforcement learning hits 81.8%, a huge jump from the original 65.8%. This impressive improvement shows that the framework successfully instills powerful reasoning skills. So what's driving this massive performance boost? These charts offer a compelling answer. The top row shows that as the model goes through its reinforcement learning, it learns to use more and more backtracks. It's literally learning to self-correct as it's trained. Then, the scatter plots on the bottom connect this behavior directly to success. They show a very strong positive correlation, meaning the more backtracks the model performs, the higher its pass at 1 score, its ability to get the right answer on the first try. This is the proof that teaching the model to backtrack is the key. And this next table provides even more direct evidence for that idea. Here the researchers ran a control experiment. They created 2 training paths. One is the ASTRO method we've been discussing, with all the self-reflection and backtracking data. The other, called direct, uses the same math problems, but without those explicit reasoning steps. Look at the final results after reinforcement learning. On every single benchmark, the ASTRO model outperforms the direct model. This experiment cleanly shows that teaching the model how to backtrack is the essential ingredient for success. So, to wrap things up, the key takeaway from the ASTRO paper is really compelling. The framework, which stands for Autoregressive Search-Taught Reasoner, provides a clear recipe for improving an LLM's reasoning. By explicitly teaching a model to think like a search algorithm, to reflect on its work and backtrack when it makes a mistake, the researchers achieved massive performance gains on very difficult math problems. This work shows that the process of reasoning is just as important to teach as the final answer itself. That's all for this week's AI Research Roundup. Thanks for tuning in.